Hey everybody, we're going to cover the last version of the t-test, the matched pairs t-test. Now, the quintessential design for a matched pairs t-test is the pretest post-test design, okay? And that's what we mean by pairing. We have the same subjects that are in the pretest, and they take the pretest, right? The same subjects in the research study take the pretest. There's some intervention in between, and they take the post-test. So that's the typical pretest post-test design. And the data are paired, right? We have the same person in the first sample and the second. Okay, there are other ways that we can do pairing, matched pairs. Twins, married couples, for example, we can pair up the responses and reaction time studies. We can measure right hand versus left hand and then test whether reaction times are better with our dominant hand or with our non-dominant hand. And the pairing, is the same person, right? It's this person's left hand score, reaction time, and the person's right hand score. So that's what we mean by matched pairs. Now, there are other ways that we might be able to match them. We might compare the crime rates between two states, say from 1980 to 2010, right? And we might match them by year, okay? And then that's pairing by year. And it turns out that we want to use this whenever we can. Why? Because it's a very powerful test. The match pairs t-test is very powerful, very robust. So it's a good one to use. The problem is we actually have to have a reason, a research reason, some feature within the data to use match pairs. So we want to use matched pairs whenever we can, but we want to make sure that it's appropriate. Now, how do we conduct this? Well, it's a two-sample test, but we run it as a one-sample test. How? Well, we get gain scores, okay? So a gain score is the post-test score minus the pre-test score. And hopefully you'll notice that if I do the subtraction in this order, post minus pre, then a positive value means there was an increase, and a negative value means there was a decrease. So the gain score is exactly what it sounds like. They've increased from pre to post if we have a positive gain. All right, now, not every research question wants a positive gain. For example, for testing cholesterol medication, we want to bring that bad cholesterol level down, right? So we would be looking in that case for a negative gain. And then how do we run this? Well, it's a one sample t-test on the gain scores. Okay, and it's run just like a one sample t-test, although in R we have a little switch we need to flip. So it's a great test, and we've already learned how to run it essentially. Okay, so let's do an example. And so we're studying if hypnosis can reduce pain, right? So we have right, randomly selected subjects, right? And so we test their pain levels prior to the hypnosis, hypnotize them, test after the hypnosis, and we see, right, that we're looking for a decrease, right? The after scores should be lower than the pre-scores. Why? Well, because they got hypnotized in between, right? So in the middle here, there's a hypnosis, and we're going to test at the 0.05 level. Awesome. There's just third row. It's the same table as before, but I've added the gain scores. And all I'm doing, right, is I'm subtracting post minus pre and get 0.2. And post minus pre and get negative 4.1. And post minus pre and getting negative 1.6. Now, that's fairly easy to accomplish in R. Okay. And yeah, we'll jump over to our notebook. Okay. And conduct this test. Okay. So, hypnosis and pain, we have the same table. Okay. And when the data is given to us, in this form instead of in a CSV file or something that we can download or upload, right? What do we have to do? We have to use the concatenate vector, right? The concatenate function to create a data vector, right? We just do C open parentheses and then we type in the data. Okay, so just being, and this is one of the challenges often of statistics and data science. It's called data scraping, right? You have to go and get the data from somewhere. And if it's on the internet, it's not always formatted how we need to use it in R or whatever, Python or whatever software we're using, right? So this is a good thing to learn that yes, I can just type in my data. I can create the data vector before. I can create the data vector after. Okay, and what I also need to do though is I need my gain scores. So here's the thing about the data checks. I don't do the data checks on the pretest scores. I don't do the data checks on the post-test scores. I create the gain scores, okay, and I do the all the diagnostics on the gain scores only. Okay, how do I get that? Well, I do after minus before. Okay, and then you can print out the gain scores and we can see, there you go. So it does all of these subtractions for us, and you can see we had done the first two or three by hand on the PowerPoint, and you see that the data, right, it's matching up. What's it doing? It's subtracting inside these data vectors component-wise. It's doing component by component. Um, so it's subtracting using vector addition and subtraction, right? Which is good for us. That's exactly what we want. And now, right, we want to do our data verification. So let's start. We need to inspect well, what do we need? We need a density plot and a box plot. Okay, and I'm going to forego doing the descriptives. We have a small data set. Okay, so I want to get right into the very things we need to make sure this data is appropriate for T procedures, right? So we're going to do plot, density, gain, and we can do a main equals, and we probably don't need this, but density plot pain scores. Or how about difference in pain scores? Because that's what we're actually looking at. The gain score is a difference, a subtraction. Okay. Now again, we notice some slight anomalies. Do we have a basic bell shape? And the answer is yes. Is there a slight skew to the right? Maybe, right? Nothing huge, but a little skew to the right possibly. So we have approximately normal. All right, jumping down to the box plot on the gain scores. Cha-ching. No outliers. Okay, so in terms of the verification, um, right, we're saying we see that the data were likely drawn from a normal or bell-shaped distribution. We also have no outliers according to in the box plot. That may be the better way to say it. Okay, so I'm going to make that markdown. Cha-ching. Okay, so we're good. We're good. We're ready to run this test. All right. And let me open up just a few more cells here. T.test. And I'm going to do the gain scores, but I'm going to do paired equals true. All right. And what were we checking for alternative? The alternative is whether or not there was a decrease, right? So this is going to be less. Alternative equals less. Oh, it wants, I can do before, comma, after. Wait, I want to do it in the other order. After, comma, before. And it will do a paired t-test, right? On the after scores, the before scores, paired equals true, alternative is less, and notice our p-value, okay? Also notice that we'll get the same exact thing if we run it as a one sample t-test, right? So I can just do t.test on the gain scores with alternative equals L. And notice that in the output, everything is the same, right? The p-value 0.0008389, 0.0008389. We get a test statistic of negative 4.9, negative 4.9, right? So it doesn't matter whether I simply run a t-test. If I have the two data vectors, the pre and the post, then I can use this paired equals true command inside the t-test to say, hey, this is match pairs data. It's not an independent samples t-test. The samples aren't independent. As a matter of fact, the same people are in both samples, one with their pretest scores, one with their post-test scores. So it's a matched pairs design. Paired equals true will tell R to calculate the correct statistic here. So either way works. It is running a one sample t-test on the gain scores either way. So let me delete this one. And why? Well, because I'm going to do my reporting out, right? So switch to Markdown and a reporting out. What have we found? Because the p-value, right? So p equals 0.0008389 is less than 0.05, which equals \alpha, right? We reject the null. We thus have evidence for the alternative, which indicates, let's say, that we have evidence that hypnosis helped to reduce pain on average for these patients. Okay, so we're rejecting the null. That means we have evidence for the alternative. And did I set that up? No, I didn't. Let's jump back up. Why? Because that hypothesis is a little bit important. So perhaps I should have started here, but let me explain. 1, 2, 3, we'll do hypothesis. Okay, and again, in the $ mathematics equation editor, we're going to start with H subscript 0 colon / mu, and I'm going to do a mu sub g. Why? Because it's the average gain score. So the subscript g will refer to the gain score. And why am I saying that the average gain score equals 0? Put that in Markdown so you can see it. Okay. Well, if you think about it, if there is no difference between the pretest and the post-test for a person, the difference is 0, right? When I subtract post minus pre, I get 0. So that's the null hypothesis, that there was no change due to the thing that happened, right? Due to the intervention. And here the intervention was the hypnosis, right? They measure the pain levels, then they do the hypnosis, and then they measure the pain levels again. And if the hypnosis is causing no effect at all, right, we're going to have a 0 gain. What did we think? We thought we would have a negative gain, right? That the pain scores would be going down. So as always, I'm going to copy paste when I can. And H sub A, that's the alternative hypothesis, mu sub G, we think is going to be less than 0, right? We think that the gain scores are going to decrease. We're going to have negative values, meaning that after the hypnosis, the pain scores were lower than before the hypnosis. And again, whenever we're measuring something, we try to measure it in a way that higher numbers mean higher levels of that thing, right? So if we're talking about pain, we're going to try to measure in a way where a pain of 10 means they hurt worse than if they report a pain level of 5, right? So as and that just makes sense. It frustrates me when, I see research done where they reverse that and lower numbers mean higher scores, higher pain levels. That just doesn't make sense. So we have done it correctly here. So that's where the reporting out makes sense. When we rejected the null, what did we have? We have an alternative hypothesis which indicated that the pain scores had gone down. Okay, that means since the pain had gone down, and everything else, if the research protocols are done correctly, is held the same, right? Everything else is held constant. So what changed? The hypnosis. So we have evidence that the hypnosis worked, that the hypnosis helped to reduce pain. Okay, so that's how it goes. Stress. Again, let's quickly do the hypothesis and make sure that we understand that. Again, I'm going to use mu sub g. Some people use mu sub d for difference, and that's true, right? If we have a twin study, we're doing the difference. It isn't pre minus post. There isn't a gain. If you do married couples or reaction time, it isn't pre versus post. I tend to use mu sub g just because that's what makes sense in my little brain. So again, you will see mu sub d, and you will see people who don't have a subscript at all. Here we're talking about stress scores, and does stress go up when it's measured in the second week of classes? And then there's that week in the middle of the semester where there's a test or a paper due or a project due in nearly every class, right? There is that week. We measured the stress levels again during that midterm week. So what do we think? We think that the midterm stress is going to be higher, that these gain scores will be positive, right? Sorry, I need to switch to Markdown. Okay, and we will also need to do our data verification. Oh, and sorry, this is not right because it's \alpha. There, got close. Oh, level needs to be outside there. Okay. But notice that this is in the personality data set, and I didn't preload this because this is something that we do need to get good at. Okay, so let me put this down here. And let's load this data. Okay, so we're gonna put the personality data set in this variable PERS. What I'm gonna do, I'm gonna use the function read.csv. And remember, the URL has to go inside the parentheses and inside quotation marks. And I just type out the URL, https://faculty.ung.edu/rsyn, that's my name, RSINN, data, and then personality.csv. Okay, why am I doing this? Because this is something you need to know how to do. Again, we've got to be able to scrape the data from the internet. So we need a way to grab it from the internet when it's in a CSV file. And again, I'll open up some extra cells down there so we have room to work. And this was Markdown. It needs to be code so it actually loads the data, right? And then what am I doing? Okay, I am doing data verification, right, which is a density plot and a box plot. Okay, and I need to do it for both, right? So what am I going to do? I'm going to do layout matrix C1 1 1 1. I don't know. I see it done both ways, 1 2 3 4, identifying the slots that way. We're going to say, hey, the number of columns is equal to 2. and we'll do the LCM is about 8. Remember, anywhere between 8 and 12 will probably work, depending on the data sets. So what are we going to do? We're going to do a plot density. Oh, we don't have these out. Okay, so sorry, S1, right? We need to do first $sign stress 1. Okay, and S2 is going to be the same thing, but for the stress 2 variable. Sorry about that. So now we've loaded the data frame in, and we're extracting S1 and S2, these columns, right? And when I do this density plot for S1, for example, and then let's do title main equals, we'll say density stress 1 scores. Okay, and close parentheses. And why am I going to just copy paste? Well, the next one is just I want to do the same thing, but for S2. So I'm going to change this to stress 2 scores. Okay, and then I'm going to do a box plot. But you know what I can do here? I can do a box plot where, well, okay, box plot S1, box plot S2. And again, let me copy paste a title into the box plot. We want to be able to tell the box plots apart too. Once they're graphed, that gets a little harder. Okay, and copy paste that into the S2, change this to stress 2. And there we go. We get a nice grid, a 2x2 grid, and you can see stress 1, no outliers. And is this bell-shaped data? Well, that's on the borderline, I have to admit. I'm going to say we're okay. This one looks more bell-shaped. Again, both of them have this second mode kind of emerging. This one doesn't seem to have a long enough tail to the right. It's just barely visible. So we have some question marks with stress 1. Stress 2 is good. Oh, but we weren't supposed to do the analysis here, right? We aren't doing a 2-sample independent samples t-test, correct? So that's the danger. I don't want to do the data verification on both samples. I want to do the data verification on the gain scores. Okay, so let's reconfigure. Okay, and I'm only going to have 2 slots in the matrix, right? Why? Because I am doing the density for the gain and the box plot for the gain. So I can delete a density plot, I can delete another box plot, and these are gain scores. Oops, I meant to capitalize G there. And okay, and then when we run that, now when we combine the samples and subtract, you'll notice that we have a much better looking bell curve. Again, do we have extra data piling up in a couple places that creates some minor anomalies? Yes. Do we have evidence of a tail to the left? Yes. Do we have evidence of a tail to the right? Yes. Do we have any outliers in the box plot? No. Okay, so our data checks actually work out. And they work out a lot better when I do them on the gain scores. Again, the original scores and the pretest scores, the post-test scores, that's not where we run the diagnostics. We run the diagnostics on the gain scores, and that's important. So we're going to say we have approximately normal data with no outliers. Thus, these data are appropriate. or, and I'll just say T procedures. We only have one specific T procedure that we want to do at the moment, but that will cover our bases, okay? So we have a hypothesis. We're looking for an increase, okay? And by the way, sorry. I'm gonna have to think about how I did this. Gain is actually, I'm sorry, gain is actually working from above. I need this. I need gain is equal to S2 minus S1. It's still using the old gain vector. Now, okay, we have a problem, a slight problem. Okay. Again, you'll see that the bell shape, very good here. But dang it, we have an outlier to the right and an outlier to the left. Now notice they're not that severe. They're a little. They're both clearly outliers, but we have balancing outliers, and we have a sample size of 129. Okay, so my apologies on not updating the gain scores, right? So I'm going to change this, right? We don't have no outliers. We have with an outlier to the left and one to the right. The outliers are balanced to a degree, and the sample size is n equals 129. Okay, so for the reasons I mentioned, we're still okay, right? These data are still appropriate for T procedures, okay? And let's just highlight that in bold. Okay, these data are appropriate for T procedures, even though they're outliers. Now, they cause some concern, right? But again, with a sample size of n equals 129, that's going to be fine, right? Remember our data checks. That's still okay. Okay, so now we get to run the test, right? So I'm going to run t.test, and I can run it on the gain scores, right? T-test.gain, and then my alternative hypothesis is greater. We think that stress will go up. And there you go. There are the results. And hey, look at this, right? Our p-value. Sorry, I thought I had the highlighter there. Didn't mean to cross that out. All right, right. The p-value is less than 0.01 even. And so we're going to reject the null, right? Let's write that out. Reporting out here is going to be because p equals 0.007858, which is less than 0.05, which equals our backslash alpha. We reject the null. We have evidence that stress increased during midterms. And again, you're probably laughing at me. They're like, of course, stress increased during midterms. And I know there were some reasons we did this test, but it does confirm what we suspected from the very start, that yeah, stress is higher during midterms. During that point in the semester when everything's due and there are tests, yes, students become more stressed. The key thing to remember about a matched pairs t-test, well, there's a couple of things, right? It's very accurate, right? We want to use it. It's accurate and powerful, and we want to use it when we can. However, there has to be a reason to pair up the pretest and post-test scores, or if we have a twin study, there has to be a way to pair the data, or we cannot do it, okay? So, and when we do have a paired match pairs t-test, it is conducted like a one-sample t-test, right? And that will conclude what we talk about with the t-test. Thanks.